We've been talking a little bit about differentiability, and we've been talking about how there are some functions that are not differentiable in certain places. We're going to look at it sort of in a different way today, and we're going to look at our calculator and think about differentiability slightly differently. So in the past, we said that when a function has a corner, a cusp, a vertical tangent, a discontinuity, it's not differentiable. We're going to look at something from a different perspective, and we're going to talk about why those functions would not be what's called locally linear. So, locally linear, what does that mean? We already know that taking the derivative of a function means find the slope of a curve at a single point. This process is based upon the fact that if you zoom in really close to any function, then even the curviest functions will look like a straight line. Using this idea, we say that functions are what's called locally linear. Think about the word as meaning local as meaning very close. So if I say I'm going to like my local grocery store, it means it's close to my house. If we zoom in very close, every graph looks like a line. Therefore, another way to think about places where a function does not have a derivative is that the function does not look like a line when you zoom in really close. So what we're going to do right now is we're going to use our calculator. We're going to look at the graph, and we're going to figure out whether or not these functions are differentiable at 0 by zooming in really close and seeing if they look like a line. So first we're going to graph. To graph the absolute value, you just have to go to the math button, which is right here below alpha. And then if you use the right arrow to the number menu, the first option is absolute value. So I'm going to graph the absolute value of x plus 1, and I'm going to go to zoom 6 to sort of reset it back to normal. So are we cool here with that? This is the graph of absolute value shifted up one space. Now we're going to zoom, and we're going to zoom in. So move it so your little blinker is really close to where that corner is, and hit enter. We zoomed in. Now we're going to zoom in again. We got to zoom in like a lot of times. So zoom in, enter. Oh. Zoom in, enter. You might need to move your little blinker around a lot of times. Zoom in, enter. To get it really close to that corner, zoom in, enter. Is it getting any straighter? Does it look any more like a line? The answer is no. Turns out no matter how close you zoom in to an absolute value graph, it's never going to look like a straight line. That's why we said that this one has a corner. It's not differentiable. It's another way to think about it. So we would say here it is not differentiable because it never looks like a line. It never becomes linear. Now let's try this graph. So go to y equals, clear it, the square root of x squared plus 0.0001 plus 0.99. Zoom 6, just reset it to home base. Still kind of looks like an absolute value graph. But let's zoom in on this one. Zoom in, get close to that corner, move your little blinker, hit enter. Now we got to zoom in again because we got to zoom in really close. Move your little blinker close, hit enter. Oh, it's kind of looking a little bit curved there. It's not quite so sharp. Let's zoom in again. Hit enter. Now it really kind of looks curvy there. Zoom in again, enter. Oh, it got a little bit off the screen. We're going to zoom in again. I got to go way down here. Oh, did my calculator just die? No, I just made it. I just made it too shallow, like brightness-wise. No. Enter. Ooh, it's really curvy now. We're going to zoom in again. I got to go way down here. I got to get very close to that little valley. Enter. Oh my gosh, it's like flattening out. It's not quite so sharp. Zoom in again. Hit enter. It looks basically like a straight line. Zoom in one more time, enter. It just looks like a straight line. There's no curve to it at all. So this one is differentiable. Because it is locally linear. Now, if you think back, both of these graphs started off looking kind of the same. But because of the way an absolute value graph works, no matter how many times we zoom in, it's always a corner. Because of the way this graph works, when we zoom in far enough, it's not a corner anymore. Now, it turns out our calculator can also help us to get derivatives in another way. Our calculator has a function built into it called n-derive. This function will allow us to find derivatives at specific values without having to use a limit anymore. So we have learned how to solve problems like this without a calculator. Find the derivative of this function at x equals 2. So let's do it. The limit as x approaches 2 of f of x minus f of 2 all over x minus 2. Which means we get the limit as x approaches 2 of 1 over x minus 1 over 2 all over x minus 2. Let's solve this by making a common denominator. So if I draw in my denominators here, my common denominator will be 2x, and I'm going to distribute that to everybody. I get the limit as x approaches 2 of, first the x's cancel, so it's 2. Then the 2's cancel, so it's x. Then nothing cancels, so it's 2 times x minus 2. We said that in order to make the 2 minus x on the top and the x minus 2 cancel, we have to factor out a negative 1. So if we cancel the x minus 2's, we get the limit as x approaches 2 of negative 1 over 2x. Now we can just plug in our 2, and we get negative 1/4. That's fine. If you don't have a calculator, that's kind of what you have to do. But if you have a calculator, it'll do that for you. Now I want to make this very clear here. This only works for specific values. Your calculator will not give you a derivative function that's a general function. So if you ever says like find a general derivative, you have to use a limit to do that. But here's how you do it. Are you ready? Go to math. So let me write this down. First, we're going to go to math. If you go down, you should see that option 8 says n-derive. So you can actually just push the number 8. Now you're going to type in d over d, and you need to type in the x. Remember, that's one of our notations for take the derivative. Then there's a parentheses, and you need to fill in the function. So in this problem, the function would be 1 over x. Then there's a line, and there's an x equals, and you need to fill in the number you want to calculate. Since we want x to equal 2, we would just type in 2 and hit enter. Now it says negative 0.25, blah, 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 a bunch of stuff. Your calculator is using a limit, it's estimating, but it's a pretty good estimate. So can we agree that negative 0.25 is pretty close to negative 1/4? That's our answer. You'll notice that negative 1/4 matches negative 1/4, so you're good. Some more stuff, like just general good to know information. Let's practice using our calculator to find a derivative. So for this problem, we're going to go back to math. We're going to push the number 8. Like, don't keep going down, 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 down. Just hit 8. We're going to type in the x, type in the x to the 3rd power, type in the 2, hit enter. Your answer is 12. If you would like to, this is a good time to pause the video and try number 2 on your own and see if you can do it. So math option 8, d over dx, x squared minus 4x plus 7. Fill in the 3 because remember this means that our x value is 3. Enter, you get 2. Pretty easy, I like that. Here's another cool thing your calculator can do for you. This whole day is just like cool stuff your calculator can do. Use the graph of the derivative. So we can actually tell our calculator to draw us the graph of the derivative function. And then by looking at the graph sometimes we can tell what the derivative should be. Like the general function. So, in number 3, we were going to graph the derivative of 2x. So go to y equals. Go to math option 8. So we've got that derivative function in our y equals now. We're going to type in the x. We're going to type in the 2x. And then here, instead of putting a specific number, we put in an x. So here the only change is that we're doing d over dx, parentheses, we're going to put the function in there, and then we're putting x equals x, and again this is all going in our y equals. Now if I go to zoom 6, which is like standard zoom, you'll notice it's drawing the graph and it's doing it very slowly. It's basically calculating a whole bunch of derivative values and graphing them for you. If you'll notice, the graph of this looks like a horizontal line. Specifically, it's a horizontal line located at the value 2. Think about the graph of this original. This original is a line whose slope is 2. So because the slope is 2 all the time, all of these y values are 2 all of the time. So the answer here for your derivative function, your general function, would be that f prime of x is just equal to 2. It's a constant. The slope is always the same. If we look at problem 4, we're going to do the same thing. Go back to your y equals, change 2x to ln of x. And then zoom 6. Now if you look very carefully at this graph, it looks like this, which looks like one part of the 1 over x function. The 1 over x function has another part that's over here. So the derivative would just be 1 over x. The reason you're only getting one part of it is because the domain of ln is just the positive x values. So it's just this half of the graph. Let's try number 5. This would be a good place to pause if you think it would be helpful. X squared, zoom 6, we're going to take a look at it. Ooh, it looks like a line. In order to write the equation of that line, we need to know two things. We need to know the y-intercept, and we need to know the slope. The y-intercept is pretty easy to figure out. If I just click trace and I type in 0 for x, I get that the y-intercept is 0. But then, if I go to my table, I can actually look at the x and the y values and see if I can figure out the slope. So the slope, the y values are going up by 2 every time. The slope would be 2, which means the derivative would be that y prime, or f prime, is 2x. It's a line. Just sort of a cool thing your calculator can do. I'm never going to ask you to do this on a test or something. It will be in your homework, but I think it's kind of cool. Now your calculator is also a liar. Turns out that when you find the derivative on your calculator, sometimes it lies to you. Let's think about what we already know. Do we think that the derivative exists at x equals 0 for this graph? Well, since it's an absolute value graph, it's going to have a corner at x equals 0. So we would say no, because there's a corner. But if we go to our function on here, and we do math option 8, and we say, hey, please take the derivative of this absolute value function at x equals 0 for me. My calculator is going to say, oh, the answer is 0. Liar. Basically, your calculator is using limits to find these things. So it means that when your calculator is trying to find the derivative at a place where it doesn't exist, you cannot depend on your calculator. Make sure you always use your brain to think logically about the problem first, and your calculator to do the problem for you second. Last but not least, differentiability and continuity. If you have a derivative, then you must be continuous, because discontinuities mean there's no derivative. So kind of a, well, yeah, duh. So suppose you know that the derivative of this function at the number 2 is 7. What else can you say about this function at the number 2? I can also say that I am continuous. Continuous at x equals 2. If you've got a derivative, you also have to be continuous. We learned about the intermediate value theorem before. Turns out it still works. So, if there are any 2 points on an interval where we're differentiable the whole time, then we can say that if C is between f prime of the beginning and f prime of the end, then the derivative has to equal that number somewhere between A and B. Here's how we use that. Can I guarantee that the derivative ever equals 2 between 0 and 3 for this function? Well, let's check. What is the derivative at 0 and what is the derivative at 3? Let's see. Using my calculator, because it can do that now, math option 8, my function is x squared. I'm going to find the derivative at 0 when I get 0. I'm going to do the same thing, math option 8. My function is x squared. I'm going to get the derivative at 3, and I get 6. The number 2 is between 0 and 6. So yes, the derivative has to equal 2 between 0 and 3 by the intermediate value theorem. Now what about on the interval between -2 and 2? Let's just find those derivatives. The derivative at -2 is going to be -4. And the derivative at +2 is going to be +4. Since the number 2 is between here, you would say, yes! The derivative has to equal 2 between 0 and 3 by the intermediate value theorem. All right, we're going to stop there. Not going to do another one. Just kind of to give you a brief summary of today's lesson, it's just cool stuff your calculator can do. It can find out if we're locally linear. It can graph derivatives for us. It can calculate derivatives for us. It sometimes is a liar, so watch out for that. Other than that, just some sort of just stuff that you need to know. See you tomorrow.